Hey guys, my name is Alan Yoon, and this is Physics Lab 4. The goal of this lab is to track and model the path of a spring mass system as the mass swings in an oscillating arc-like motion. The main principles we will use in this lab are the momentum principle and the energy principle, along with an application of spring physics. The momentum principle will again be used to update velocity and position. The energy principle is to analyze the energy transfers in our system, consisting of the mass, the spring, and the Earth. And the spring properties are applicable to a spring system. In the end, we see that the tracked and the modeled paths are very similar. The differences arise from the forces being gradually dissipated by the drag force, which was unaccounted for in the model. The clip begins just after the spring begins its motion. The mass falls from rest, so the initial velocity is 0. We begin at frame 5 and end at frame 101, with each frame measuring about 1/10 of a second. The analysis was calibrated using the still length of the spring of 0.7 meters. The axis was placed so that the origin is on the attachment point of the spring and oriented normally so that the positive y-axis is up and the positive x-axis is to the right. After tracking all of the points in each frame, we export a CSV file of all of our track data shown here to be used later in our model. Looking at the graphs of the data shown in the top right, we can estimate the periods for both the x and y motion. This is a good time to discuss our second what does it mean question. By seeing the change in time between 2 points of equal relative position, the x period is estimated to be 1.71 seconds and the y period is estimated to be 1.52 seconds. This shows that the x motion does not make a whole loop in the same time as the y motion. The combination of energy along the x and y motions are not uniform and are ever changing. This will be visualized and explained later. Now let's move on to build our computational model using fundamental principles of physics. These first blocks of code simply initialize the model. We have initial conditions taken from the video, and we also read in the CSV file taken from our tracker data. The mass, the spring constant, and the relaxed length of the spring were all obtained from the lecture videos. Lastly, here are some initial spring conditions which will be clarified later. Our first fundamental principle is again the momentum principle, which we have basically beaten to death at this point. In our system, we calculate F net from the force of gravity and the force of the spring. Then we apply these derivations of Newton's second law to update velocity and position. Next, we have to implement spring physics since we are using a spring. The force exerted by the spring is measured by some spring constant multiplied by the difference from the relaxed length of the spring. In our code, we have to constantly update the ever-changing length and direction of the spring force. Before, we saw the initial state calculated, and this block updates those values in our while loop. Next, we cover the energy principle. It states that in a closed system, energy changes to the system can only be caused by work done by an outside entity. In our system, defined by the mass, the spring, and the Earth, no work is being done to the system as seen here. The energy in the system remains constant, so the total change in energy is 0, as seen here. However, the energy can change forms, in this case from potential to kinetic and vice versa. The sources of potential energy come from the spring and gravity. As potential energy decreases, it changes to kinetic in the form of faster velocity. As velocity and kinetic energy decrease, potential energy increases. In our code, we calculate these energies to display graphically. We first calculate an initial kinetic, gravitational potential, and spring potential energies. Then we update them in our while loop. All the changes in energy are plotted on a graph which will be analyzed soon. Now that we have all the physics accounted for, let's look at our code as a whole. We see the visualizations, the initial conditions that were previously discussed, and then we see the while loop that applies the momentum principle, spring physics, and the energy principle. We see the graph being constantly generated in the while loop, and this final part creates a second ball using the position data taken from our CSV file. This allows for direct comparison between the tracked and the model data. Now let's run the model and see what we get. The blue ball is the model and the red ball is the tracker data. The blue arrow is the ever-changing spring force and the black arrow is a constant force of gravity. The red ball was jumpy since it only has data at fixed points, not a consistently iterated track. Overall, the motion is very similar. We can see this extra clearly by slightly adjusting our code and outputting the y-axis motion separately. We see that the model is in blue and the observed is in red. We see the periods very well aligned. The discrepancies, however, are caused by the mass slowing down because of drag. The amplitude of the observed y motion is gradually decreasing because it doesn't go as high since the energy is being dissipated. If our model were to be improved somehow, we could account for this drag force. Now back to the energy graph generated by our model, we see the kinetic energy in blue, the spring potential in red, and the gravitational potential in green. As the gravitational potential goes up, spring potential goes down, which makes sense considering height off the ground. However, we see that these energies are overall not consistent throughout the domain. To expand on the second what does it mean question, if we remember when analyzing the sinusoidal curves from the tracker model, the periods for the x motion and y motion were not equal. This explains why the energy graph generated by the model is non-consistent. Sometimes there's more kinetic, sometimes there's more potential, etc. However, to address the first what does it mean question, the energy principle is still satisfied. As all of the other components are ever changing, the total change in energy of the system, as displayed by this yellow line, remains zero. So the energy of the system does not change. That's it for Lab 4. In conclusion, we have confirmed the energy principle at work in the spring mass system. We have accurately modeled the observed motion with area arising from only an unaccounted drag force. Thank you.